we recall again that the area under the constant velocity versus time graph gave us the displacement. Let's see if that might not be true for a graph where the velocity is changing. If we take the area under this graph, we see that we have a trapezoid here. Now I know that this is a triangle, but I'm going to talk about trapezoids because it's more general. A triangle is nothing but a trapezoid where one side is 0. And I'm being a little bit careless with my terminology. We have a right trapezoid because we have a right angle here. But let's be sure, let's not worry too much about those details. That's always what we're going to be dealing with when we deal with graphs. The area is going to be the average altitude by the width. Now the average altitude of this trapezoid is the altitude at the midpoint, the altitude here. And that average altitude, we can see very clearly, is probably right at 4 meters per second. If we multiply that average altitude, the average of the left and the right altitudes, by the width being from 0 to 4 seconds, a time interval of 4 seconds, we're going to have 4 meters per second multiplied by 4 seconds, or 16 meters. So we see that the area of this graph, under this graph, is 16 meters. Of course, that's exactly what we got over here when we calculated the displacement. In fact, we've really done the same calculation because the average velocity up here is the same as the average altitude of this triangle. I said a triangle, it's a trapezoid, it's also a triangle. The average altitude is the average of whatever quantity is on the vertical axis, which in this case is velocity. So the average altitude is the average velocity of the triangle, the average velocity of the object. We multiply that by the width, which of course, as we've seen, is the time interval.